So, voltage. Start out with a little bit of review. So, I gave you a big planetary charge and a point away from it, a field point, as we call it, somewhere in the electric field. And so the first thing this asks in part A is, it says, hey, find the electric field, magnitude and direction, 75 centimeters east of a 2 microcoulomb charge. Okay. You may want your formula sheet handy. You may not. I don't know. Electric field, we had two ways of calculating. Electric field, symbol E, was KQ over R squared, or that, force divided by Q. This was if you knew the charge at the field location. Have they told me what charge is sitting right there? Nope. Instead, what they've told me is the planetary charge that's causing the electric field. Did somebody back there say, yep? And I said, no. They haven't told me the charge that's sitting here. They've told me what's causing it. I use this one if I know what's feeling the electric field, what the charge at that location is feeling, and a force. They haven't given me a force here. They've given me a distance, a radius. They've given me the planetary charge. I'm going to use KQ over R squared. It's going to be 9 times 10 to the 9th. The charge is 2 coulomb. That little mu symbol means microcoulombs, not to be confused with an M, which is milli. And careful, not 75. I got to go to meters. 0.75 squared. No, millicoulombs is 10 to the negative 3. Lowercase m, milli, 10 to the negative 3. Micro, 10 to the negative 6. Of course, you don't have to memorize that because it's all sitting on that little chart right there, right? You get 32,000? No? Yes? Units for electric field, what was it? Psst. Units for electric field, it's derivable right from there. What was it? Newtons per coulomb. Direction, because it did say direction. How do I figure out the direction of the electric field at that field point? I ask myself a question. What question do I ask myself? If I put a positive right there, which way is it going to want to move? So that if I put a little positive test charge right there, which way would it want to move because of that big planetary charge? It looks like they said east, so can you tell me in terms of east and west? If the question says east, I'll use east. If the question says left and right, I'll use left and right or away or something like that. Right? I'll try to be consistent. Okay. 32,000 newtons per coulomb to the east, B. Going to skip B. C, because it's the same question. C says, find the force on a 2 coulomb charge placed at that point. So now, Joel, we're imagining that there is a charge sitting right there. How big? Joel, how big? 2 coulombs. Huge. I think I told you, like 2 coulombs probably would kill you. 50 coulombs certainly would kill you. 2 coulombs, it would almost certainly, like if you had that all go into you all at once in a big, probably you'd be getting 3rd-degree burns and your hair would melt and it would be disgusting. Okay? So a huge charge. What does it want me to find in part C, Joel? Okay, there's 2 ways to do this. I could go, write this down, because I do know, okay, 9 times 10 to the 9th. Charge 1 is the 2 microcoulombs. Charge 2 is the 2 coulombs, and R is 0.75. And if I hadn't done A already, I would do that. But Jacob, there is a shortcut. You may notice on our formula sheet, there's another equation in the same row that has force in it. Which one, Callum? Get the F by itself. You see, I could also go F equals Q, the charge at that location, times the electric field at that location. And why would I choose to do this as a shortcut? Because what did I find in part A, Sean? The electric field at that location. Which really, Sean, means this. It's going to be 2 times 32,000. Sean, I would argue you can do that in your head. 60, you know what? That's the 64,000 Newton question. That's a huge, pretty huge force, too. Well, it's because it's a pretty huge charge. But what I want you to realize is, hey, I got 2 ways to find a force. You give me 2 points, yeah, I can. It's just like Newton's law of universal gravitation. I can go blah, blah, blah. But you know what? Just like we also were able to find gravity before we knew Newton's law of universal gravitation by going m little g, we can go Q big E. That's exactly the same as for gravity going mg. There's our shortcut because we know the gravitational field strength for this one. We know the electric field strength for that one. Is that okay? I'm even going to skip D. It'd be the same approach, and I'd still probably go QE. What I want you to realize, Jordan, is, hey, if I know the electric field of that location, I got a built-in little shortcut. Yeah. The electric field tells us the newtons of force per coulomb at that location. And it turns out for energy, there's a similar and analogous concept. It tells us how many joules of energy each coulomb possesses at that location. Electric field tells us how many newtons of force each coulomb will feel at that location. Potential, also called voltage, tells us how many joules of energy each coulomb has at that location. Now, there's a problem. Potential tells us how much potential energy per coulomb, but it's not energy. And there is, no pun intended, lots of potential for kids to potentially get potential and potential energy mixed up. They're similar, they overlap, but they're different ideas. Potential energy is measured in joules. Potential, or voltage, is measured in, well, we call it voltage. What do you think it's measured in? Volts. I prefer the term voltage, but it's pretty clear the literature prefers the term potential. I think that just opens the door up to getting potential and potential energy mixed up. Suck it up, people. It's what we go with, okay? So the units of potential or voltage is joules per coulomb. It's how many joules each coulomb of energy has at that location. It's joules per coulomb, which really means voltage is defined as potential energy divided by the charge, because that is joules per coulomb. I wrote down here the understatement of the year. We must be careful not to confuse potential with potential energy. One's in joules per coulomb, one's in joules. And you know what? I believe that equation is on your formula, although I think on your formula sheet, what they've said is the change in voltage, the change in potential is equal to the change in energy. Okay, they've added a final minus initial little dealie, so let's put the little delta in front there, but it comes out of basically our definition of voltage. It's how much energy each coulomb of charge has. So if there's 15,000 volts at one location, what you're saying is every coulomb of charge has 15,000 joules of energy. If there's 30,000 volts at a location, you're saying every coulomb of charge has 30,000 joules of energy. Example 2. Fill in the proof to find the potential or voltage equation for a point charge Q. Okay. We imagine that we move a test charge Q to the field point, and then we find the ratio potential energy per charge. We said potential energy was this, K, big Q, little q over R, where big Q is the big planetary charge and little q is the tiny one that we're moving. Voltage is the energy divided by Q. Voltage is the energy divided by Q. What's on the bottom of that equation, Seb? Is there a little q on the top too? This is the equation to calculate voltage. So it's defined as how much energy per coulomb, and by actually plugging into two equations, you end up with, oh, turns out voltage is K big Q over R, where Q is the charge that's creating the voltage, and R is how far away you are from the charge that's creating the voltage. Put your pencils down. There is room for this to get a little bit ugly, unfortunately. Get out your formula sheet if you have one, or look up. I'm going to go to my formula sheet here. There is room for this to get a bit yucky because here are our electrostatics formulas. And you will notice that the equation for force looks an awful lot like the equation for electric field, looks an awful lot like the equation for potential energy, which also has an E there, which is why I never use E for energy, which is why already in grade 11 I start using PE and KE, because I can see this coming down the pipe and I want to try and prevent that, which also looks an awful lot like voltage. In fact, kids get these two mixed up, because they're called potential energy and potential. And you know what? This is why at the beginning of this unit I said this is not the unit you want to try and cram and learn at the last minute. Because I guarantee you do that, Jacob, then on the test I'm going to say find the potential, and you're going to give me the potential energy, and I have to give you 0 out of 7. Because it's as though I said find the force and you told me the speed. They may look the same and the equations may have some overlapping units, but you found totally the wrong thing. This is why also I suggested keep your formula sheet out for this unit. Train your eyes to even look in the right location. Grasping at straws, but I'm desperate. Okay. Let's try some of this. Oh, little note. Voltage, scalar or vector. What did I write in the box above? I think I put it there. Oh, I did not. Oh, yeah. Volts, scalar. Voltage is a scalar, so include the plus or minus. Scalars, signs. You can have a negative voltage, you can have a positive voltage. In fact, usually we're going to be interested in the change in voltage between two locations. We're going to call that the potential difference. So, example 3. Same diagram as before. It says, find the potential, the voltage, 75 centimeters east of a 2 microcoulomb charge. Okay. Voltage. Now, I developed a habit a long time ago. Later on, we're going to be doing equations that have voltage and speed in them. The problem is my uppercase and my lowercase v's look very, very similar if I'm writing fast. So when I was in university, my prof, to distinguish between an uppercase V and a lowercase v, turned an uppercase V into a fonted V. I'm always going to add those little wings. That's going to be my V voltage uppercase, so you'll always be able to tell. You don't have to, but it's a good habit to get into, trust me. Voltage is equal to KQ over R. 9 times 10 to the 9th. The charge that's causing everything is 2 microcoulombs, and our distance is 0.75. I might be able to do this in my head. 9 times 2 is 18. Dividing by 0.75 is the same as dividing by 3/4, the same as timesing by 4/3. 18 divided by 3 is 6 times 24,000? Double check me. Yeah? Units. Joules per coulomb, which is defined as a volt. Again, we're going to cross out B. Dunk. We're going to do C. AJ, what does C want me to find? Potential energy. Now, I can do this 2 ways. I could go from last day, hey, potential energy is K, Q1, Q2 over R, and that's perfectly acceptable. And I would do that if I hadn't done part A already. But what did I find in part A? The voltage at that location. If you recall, on the previous page, we defined voltage as energy per coulomb. Could you get the energy by itself for me in that equation, please?
Times by P. Times by Q.
Times by Q. Another way to calculate energy is if I happen to know the voltage at that location, and you tell me the charge that we're putting at that location, I can just do that as a shortcut. Riley, I would do that if I had already happened to find the voltage at that location. Otherwise, I could do it the long way, and I'll get the same answer. You can try crunching it later if you want to. But I can then say, okay, so potential energy is going to be 2 times 24,000. A 2 coulomb charge would have 48,000 joules of energy. Why? Because every coulomb of charge at that location has 24,000 joules of energy, because that's the definition of voltage. It has 24,000 joules per coulomb, 24,000 volts. We'll skip D. So, if I know the change in voltage, or potential difference, what's change in anything? What's change in anything? Did you say minus? What's another word in math for minus? What's another word for voltage? Hey, potential difference, that's the archaic electric term for change in voltage, final minus initial. So they'll say, hey, what's the potential difference? What they're really saying is, what's the change in voltage?
Spencer Neely to the office.
Okay.
Spencer Neely.
So we can then find the work required to move a charge between these 2 points. Example 4. This is the diagram that I think I told you guys about during the electric field lesson, or during the energy lesson, where I said, this looks terrifying. No, voltage is a scalar. I don't need angles. I don't care. All I need are the distances. So you ready? A says, find the potential. What's another word for potential? Voltage at location X. There's 2 charges creating a voltage, the left-hand charge and the right-hand charge. What do you notice about those 2 charges when I compare them to each other? They're the same. What do you notice about their distances from location X when you compare those distances to each other? They're the... Okay, so I'm going to make a little note here. Let's call this charge 1. Let's call this charge 2. Because Q1 equals Q2, R1 equals R2, find the voltage from charge 1. I'll call that V1. And then we'll just double it. Because it's a scalar. I don't care about any angle. I'll just double it. It's a scalar. Is that okay, Sammy? If they had given me different charges, I would go KQ over R for the first charge, KQ over R for the second charge. But then I would still just add them up because it's a scalar. So I don't care about doing any tip-to-tail garbage. So I'm going to find voltage 1, which is KQ1 over R1. It's going to be 9 times 10 to the 9th. Positive 2.5 microcoulombs all over. Oh, I scrolled up. 0.2. Oh, and then we're going to go times by 2 so that also gives us the voltage from charge 2. Okay, so Joel, we don't always times by, it's just the fact that these happen to be a symmetrical diagram. I'm basically going to do half the diagram and double everything. Is that okay? And again, why can I get away with that? It's a scalar. I can just add this stuff. I don't need to do any trig. What do you get? How many volts at location X? If you put a voltmeter at location X, what potential would it read? Sorry? That's after you doubled it? 200, okay, times 2, 225,000. So at location X, you know what? I called this voltage 1, and then I've gone times by 2. So let's say this is going to give us voltage X, which is 225,000 volts. Direction, scalar. B says, find the potential, the voltage at location Y. Okay. That's going to be voltage 1, but down below, KQ1 over R1. It's going to be 9 times 10 to the 9th, 2.5 times 10 to the negative 6, except make sure you use the radius, the distance to location Y. Yep.
Can I ask if you wanted the voltage in scientific notation or whatever? Not really.
2.25. You know what? That's to 3 sig figs regardless, so I'd take both. But by the way, electric fields you're going to find were often in the tens of thousands or the hundreds of thousands. Voltages you'll often find are in the thousands, sometimes in the hundreds, or in the thousands, or in the tens of thousands, or in the hundreds of thousands, rarely in the millions, just to let you know. Divided by 0.35. And then times by 2 to give us the voltage at location Y. Nine times 10 to the 9th, 2.5 times 10 to the negative 6 divided by 0.35. So there's the voltage from one of them. Double it. I get 128,571. I'm going to write that, Ryan, and then I'll go to 3 sig figs because I think I'm going to be using this for another answer. I'm going to write 128.28, Mr. Dueck. 571. Did I round off properly? Yeah. Which is 1.29 times 10 to the 5th volts. That's the voltage at location Y. Matt, what does part C want me to find? No, read carefully. I don't think it says voltage. Does it? You read part C. There's the key word. What? Difference. The change in. The change in. Now, I like change in to be final minus initial. So are we moving from X to Y or from Y to X? What's our final? What's our initial? Read part D, Matt. Where are we ending up?
From Y to X.
So where are we ending up? Oh, that's our final? So I'll make a little note here. That's our final. That's our initial. So I want to find the potential difference, the change in voltage, which is going to be the voltage at X take away the voltage at Y. Sorry, but that's what the key word there is it's a change in. We've just found the voltage in A and B. So when you said find the voltage, I'm pretty sure I already did that. But the change in, oh, and that's going to be just like you think, 225,000, take away 128,571. Do I need to go tip to tail? Why? It's a scalar. They did this diagram on purpose just to really terrify you. They could have given you a very strange diagram. Doesn't matter. Okay? So it's going to be 225,000, take away that answer. And I get the potential difference, the change in voltage, is 96429. 96429, or 9.64 times 10 to the 4th volts. Let's write it underneath, Mr. Dueck. 9.64 times 10 to the 4th volts. Right, Matt? You got why I freaked on you initially, right? Okay. Hey, Jordan, what's part D asking me to find? This Jordan.
Find the
Work. Can I go force times distance when I'm dealing with point charges? Never, because the force is always changing. Is there an area under a graph? What was my other definition of work? What was the third definition of work that we've been flogging? Yeah. Now, I could go like this. Change anything is final minus initial, and I could say, oh, that's going to be K Q1 Q2 over Rx minus K Q1. You know what? I could do that. But what did we just find in part C? Matt, what did we just find in part C? Another word for which is? I yelled at you. It's not volt. I got to be fussy. Change in, because we're talking about work. What do you see in front of the potential energy? Okay, I want to emphasize that. So what do we find in part C? The change in voltage. Hey. I have an equation that has change in voltage and potential energy in it. See it? See it? See it? This one. This one. Get the energy by itself. Times, yeah, this is kind of becoming a little familiar. I hope. Turns out, I'm going to make a little note here, and if you happen to know not the voltage, the change in voltage, the potential difference, then potential energy is Q delta V. Now, why is that so nice? Well, Q is the charge that we're moving. What does part D say? How big is the charge that we're moving? Jordan, what did you say? How big is the charge in part D that we're moving? 2 coulombs. Is it coulombs? 2.5 coulombs? Really that big? Maybe it was. I have 1.25. What do you guys have? Okay, so not 2.5. Okay. Is all of our D's the same? Yeah, okay, because I changed these questions and suddenly I thought, oh, maybe I forgot to photocopy the wrong. Okay. Right? Jordan, you with me? Yeah. We're moving we're not moving that. What does it say in D? Read D to me out loud. Find the work what?
Required to move
Which charge are we moving? Not micro. Milli. Okay? By the way, can you see there's lots of room to make mistakes here, which is why I'm picking on people not to make fun of, but I really want to make sure we avoid those. So that's the charge that I'm moving. So that's going to be 1.25 times 10 to the negative 3. And the change in voltage was 96429. I don't need to go find the potential energy from both charges at each location. Understand, if I did it that way, I would have to find the potential energy between those two charges, add them up, find the potential energy between those two charges, and between those two charges, add them up, and then subtract. I'd be doing 4 calculations. Minimum 4 lines, 2 lines. Much nicer. I happen to have this number still stored in my calculator, so I multiply that by 1.25 times 10. By the way, do you see how we figured out which one we're moving? Yes, the question will tell us. It'll say, here's the charge you're moving. The other ones are fixed. They're locked in place. They're the ones that are creating the, you can think of it in terms of gravity, the gravitational field that's making it tough. They're creating the voltage, which is allowing me, okay. 121, I guess, joules of work. So, if the charges begin and end at rest, then the work will just be the change in potential energy, which is the charge times the change in voltage. So I wrote here, prove that if a charge begins and ends at rest, then the work done in moving Q is given by that. Well, we kind of just did. We said work is equal to change in potential plus change in kinetic. If I start at rest and end at rest, what's my change in kinetic? Nothing. And we said that the change in voltage was defined as the change in potential divided by Q. I guess that means work equals Q There's my proof. Oh, and if you're still moving, fine, you'll have a half mv squared somewhere in there, because there would be a change in kinetic. You could elaborate to that too. Okay. What's voltage? It's how much energy per coulomb at that location, caused by the electric fields, attracting or repelling, all that stuff. It's a scalar, include the signs. Summary. The potential voltage can be found using the definition if we're told how much energy a test charge has at that location. So if you haven't told me the big planetary charge, if instead, Joel, we have a small little test charge at a location, well then voltage is how much energy that charge has divided by how big the charge is at that location. Or, if I know what's causing the potential energy, and therefore the voltage, if I know the big planetary charge that's creating everything, it's that. And again, for both of these, include the signs. You can have a negative voltage, not a problem. Oh, the potential energy of a system then can be found from last day, if we know both charges, or I can also find the amount of energy if I know the voltage at that location and the test charge at that location. Potential energy is also QV. Oh, and also change in potential energy is Q, change in V. So there we can get our work definition out of there too. Note, potential energy and potential, voltage, are not vectors, they are scalars. So if we have several charges contributing potential energy or voltage, just add them up. If it's joules, or add them up if it's volts. Oh, unless they say potential difference, what mathematical operation does the word difference mean? That's the fancy voltage word for a change in voltage. They just call it a potential difference. It's your homework. Number 1. 2 is good. 3 is good. 4 is good. Giving you lots of practice, but you got lots of time. 5 is good. 6 is good. Relax. I'm going to assign 7. 7 is actually going to show up in the next lesson or the lesson after that. A couple lessons from now, because I'm asking you to find its final speed. What am I asking you to find in number 7? Now, it's going through a change in voltage. You can kind of think of that as a change in height and a change in speed. I'm telling you, you can figure this out if you use conservation of energy, where kinetic energy hasn't changed. What's kinetic energy been since physics 11? Half mv squared. But the potential energy isn't being caused by gravity. The potential energy here is being caused by electrostatics. Potential energy, if you know the voltage, is... This is the equation where you're going to end up with a big V voltage and a little v speed. It's really worth using the wings. If you can figure that number 7 out. I like number 7, I like number 7, I like number 7. It's going to be on your test, but I like it so much, I'm going to do a full lesson on it later. I'm just, Joel, kind of planting a seed right now. Nine is good. Skipped 8. Find the potential. Oh, 12 is fairly good. And 14 is a little thought-provoking. I know it's lots, but you're going to get lots of time. Pause the video, and I got a little video to show you.